All right, ladies and gentlemen, you're going to be taking some notes today from the disembodied voice of Mrs. Julian to get started on our bonding unit. So you will need your bonding notes, which hopefully you have in front of you. And you're also going to need today a periodic table. So make sure you get out your reference table. You can pause the video now to make sure that everyone's got that. So we're going to need our notes and periodic table, and we're going to start talking about bonding. Now, this is only going to be a brief bit of lecture. We're going to talk about what a bond is and some basics that we need, and then you're going to be doing a group activity to get started on bonding. So today isn't going to be entirely lecture. So to start off with, big question, what's a bond? Well, if you're using the word bond in everyday life, you might talk about how you and your friend have a really deep bond. You and your friend are really bonded. Or you and your sister have a really tight bond. And it means the same thing in chemistry as it means in real life. If you're bonded with someone, it means that you're really close to them, that you have a connection with that person, that they are meaningful to you, and that you have a relationship with them that you want to keep. You're attached to them in some way. A chemical bond is very, very much the same thing. It's an attractive force that holds atoms together. So it keeps multiple atoms close to one another and keeps them connected while they sort of move around and react with other things. There are fundamentally two major types of bonds, ionic bonds and covalent bonds. There are some minor others, but these are the really two big ones that we talk about a lot. And you've already looked a little bit at ionic bonds because the lab that we did on Friday, the salt-sugar lab, salt contains ionic bonds. It was an ionic substance. Now sugar, I said that was a molecular substance. Sugar actually contains covalent bonds, that other type of bond. The whole reason, we're going to talk about why atoms bond, why do they do it to begin with, it has to do with energy. Energy will always be released when bonds are formed. This means that the atoms are actually at essentially too high of an energy on their own. And when they come together, they're getting rid of their excess energy. And we're going to have a look at that. Atoms want to bond so that they can be at a lower, more stable energy. Everything in the universe is always looking to be at low an energy point as possible. Like, I bet right now you're probably wishing that you could be back at home in bed sleeping. The reason that you kind of wish that is because that's a very low energy state, and that's what you're constantly trying to work towards. Things that are hard to do, like get up in the morning and go to school, or run around the track, run the mile for gym. Those are high energy things, and those are harder to do. So atoms, kind of just like you, are at this high energy state, and they kind of want to get to a low energy state, because when they do, they're getting rid of their excess energy and they're going to a lower energy system. On the flip side of that, when we break bonds rather than form them, energy is absorbed. This means that it will always take energy to break a bond. It will require energy to break a bond. A bond does not break on its own. That's what this is saying. Once two atoms have bonded together, they're not just going to randomly out of nowhere break that bond for no reason. It's kind of like with you and your friend. If you and your friend have a bond, have a connection, you're not just going to wake up one day and say, we're not friends anymore. We don't have that connection. No, something has to happen. You have to have a fight, or, someone lied to someone else, and something has to occur to break that bond. It doesn't break on its own. Energy is always absorbed when bonds break. And I have a little way for you to remember this, so I want you to add this into your notes. The word absorb, right, that word absorb, that's what we're going to look at. Absorb energy. Well, the word absorb has two B's, this one and this one. So energy is absorbed when bonds, for the first B, break. For the second B, energy is absorbed when bonds break. So it always takes energy to break a bond. And energy is always released when bonds are formed, when the opposite happens. Now, I'm going to have you draw some stuff out in that next section of your notes. Why atoms bond? It says, let's draw it. Atoms are far too unstable on their own. There are very few atoms in the periodic table that are actually very stable, just completely on their own, without anything, without being connected to anything else. So I want you to draw in these two little funny high energy bonds. The little lightning bolts coming off of them are showing them that showing you that they're high energy and they're unstable. And that's really the big point. Atoms are very much unstable on their own. They're high energy. But when you bring them together, when you combine these two high energy things and they form a bond, they're going to give off their excess energy. So all those little extra lightning bolts that they have when they're on their own, when you combine them, they're actually releasing that energy and they're giving that energy off. Energy is always released when bonds are formed. So show this lightning bolt leaving the system, we are losing energy, which is a good thing because it means that we're making our atoms more stable. We've got a low energy system when they're bonded together. But if I go in the opposite direction, now if I'm going to take my low energy bonded atoms, the ones on the bottom, and I want to make them go backwards, I want to turn them back from that bonded state to that atomic state where their bond is broken. Now I have to put energy into the system. Energy is absorbed. Energy is going in. This is the requiring energy to break a bond. This bond, this low energy state, it will not leave that state on its own. Something has to happen. Something has to happen to get the atoms to break their bond and go back to being sort of singletons. It requires energy to break a bond. To break a bond, we have to absorb energy. So those two B's, absorb, bonds, break. And you've got this picture on the next page of your notes. And this is sort of talking about what's happening in terms of energy and these atoms bonding. So first thing that I want to call your attention to, on the y-axis, we have energy. And so we've got low energy at the bottom and high energy on the top. And then on the x-axis, distance. And because we're talking about distance and we're talking about atoms here, we are actually going to be talking about our three concepts of charge. That one that's the closer two things are, the greater the force of attraction. The farther apart the two things are, the less the force of attraction. That does actually come into play when we're talking about atoms bonding. So notice we start here. So this is sort of like step one with the atoms, and they're too far apart. And we look at their energy, and relatively speaking, we're going to call this high energy. That the atoms, they're too unstable on their own. Notice as we're moving closer together, step two, our energy is getting lower. That's a good thing. We want our energy to be lower. We want our energy to be as low as possible. So, and then step three, we move them even closer. We have lowest possible energy. This is our bond. We've moved, look at where the atoms are relative to one another. They're touching. They are in contact with one another. They're at their lowest possible energy. That is the chemical bond. We've moved them there because the atoms, we compare them to where they started back here in terms of that amount of energy, and now they have this amount of energy. And they've lost energy. They've released energy, and that's why they formed a bond. But you'll also notice this one right here. If you move them too close, then the energy starts to skyrocket, right? It's going way, way up. And the reason for that is that we get the like repels like. When you move these atoms too close to one another, the electrons will start repelling from one another, and the nucleus, the protons, will actually start repelling from one another from the two different atoms. So you can't sort of infinitely keep on moving the atoms close to one another. You actually have to, at some point stop because we get that repulsion. So this is why atoms are bonding. It gives them a low energy state, one that they wouldn't have on their own. Valence electrons. This is a definition. Valence electrons, which you're going to see me refer to an awful lot as VE, refer to the outermost electrons, those in the very last energy level for an atom. So we're looking at their electron configuration. That's what we always check to see for valence electrons, and it's the very, very last shell. How many electrons are in the last shell of an atom? Those are what we call the valence electrons. These are the electrons that are going to be the ones that participate in bonding. And there is a super, super easy way, even easier than looking it up on the periodic table and looking at your electron configuration. There's a very easy way to determine the number of valence electrons for an atom. You find the group number, you locate the atom on the periodic table, you look at which group it's in, and the number of valence electrons will be the same as the last digit in the group number. Last digit of the group number is equal to the number of valence electrons that the atom has. For example, group 2, well, the last digit in 2 is 2, which means that all the elements that are in group 2 have 2 valence electrons. Group 13, the last digit in 13 is 3, so all the elements that are in group 13 have got 3 valence electrons. And I realize that when we talk about valence electrons, we tend to kind of ignore the transition metals, those in the middle, because their outermost electrons are in the d sublevel, and things get a little weird when we get into the d sublevel. So we tend to we're restricting this discussion realistically to alkaline earth metals, and then all the elements that are in the 13 through 18. The P block of the periodic table. So we're going to practice a little bit with this, just determining number of valence electrons. So first up is calcium. How many valence electrons do each of the following atoms have? And here's where you need your periodic table, because the first thing that you need to do is locate calcium on the periodic table. And hopefully by now you're getting a little bit more of a feel for finding elements on the periodic table, and hopefully you can find that calcium, oh, it's right there. It's in group 2. Last digit of the group number is the same as the number of valence electrons, so therefore calcium will have 2 valence electrons. That's not -2, that's just the bullet point on the PowerPoint. Next up, nitrogen. Nitrogen, N. So we got to locate N. So we're looking, and oh, there it is. Nitrogen is in group 15. Well, the last digit in 15 is 5, so therefore nitrogen has got 5 valence electrons. Tellurium, Te, same thing, you just got to find it. This one might take a little while. Find it. Tellurium. Oh, hey, look, there it is. It's a metalloid. It's in group 16. Therefore, it's got, last digit of 16 is 6 valence electrons. And krypton, not kryptonite, krypton. It's a noble gas. It's in group 18. Last digit of 18 is 8. Krypton has got 8 valence electrons. 8 valence electrons. Identifying numbers of valence electrons is very important, especially in bonding, which is why it's the very first thing that we do. Now, electron dot diagrams, aka dot diagrams, aka this might be called, sometimes be called Lewis dot structures, are a way of drawing just the valence electrons in an atom. Just valence electrons and nothing else. And it's a very, very useful means of representing an atom, because sometimes the valence electrons are the only electrons we're actually interested in. So you kind of want to have a way that just shows these particular types of electrons. The way that you draw a Lewis dot diagram, an electron dot diagram, you start by drawing the symbol for the element nice and big in the middle. So this is the dot diagram for carbon. So the symbol for carbon is C. So you draw a nice big C. Then figure out how many valence electrons it has. Carbon is in group 14, so it's got 4 valence electrons. Then the way that you draw those valence electrons, you draw them as dots. We're going to draw electrons a lot as dots. Dots or dashes. And you put the valence electrons around the symbol for the atom. But you have to put them around the symbol for the atom in a specific way. You have to put it top, bottom, left, right, or the 12 o'clock, 3 o'clock, 6 o'clock, and 9 o'clock positions. And you'll notice here that that you have to space out the valence electrons, that I didn't like put all 4 of them on the top. And the rule is that you do 1 on each side. You spread them out. Remember, it's kind of like that seats on a bus thing that we talked about with electron configuration, that electrons will sort of singly fill spaces until they have to go back and start doubling up. It's very much the same way here. You put them 1 at a time around the top, bottom, left, right positions around the symbol, and then if you have more than 4, then you go back and start pairing them up. And we're going to see that. We're going to see a couple examples of that when we try it on the next page. So my final note here, like I was just saying, you want to spread the electrons out until you have to start pairing them up. So carbon only has 4, so we're just going to put 4 single ones around it, and that's very important. You always want to spread them out until you have to go back and start pairing them up. So we're going to practice with this. Draw the electron dot diagrams for bromine, Br. Well, the very first thing that you need to do is figure out how many dots you need to draw. The dots represent the valence electrons. So you've got to first figure out how many valence electrons you have. So periodic table, Br. You got to locate Br. It's a halogen, group 17. That means bromine has got 7 valence electrons. So we're going to draw the symbol for bromine. I'm going to redraw it here. We want to place 7 dots. We're going to do it top, bottom, left, right. So I'm going to do this way. I'm going to do 1, 2, 3, 4, but I'm not done because I want to do 7. So now I'm going to go back around and I'm going to pair them up like this. This is 5, 6, and 7, and that right there is the Lewis dot diagram for bromine. Notice that when I draw my dots, I'm drawing them sort of equally close. I'm not drawing them further away. Like when I go back and repair and added in that 5, 6, and 7, I drew them flush up against the element symbol. That's important, so make sure you do that too. So that's our electron dot diagram for bromine. Next up, potassium. I'll redraw the bromine one. 1, 2, 3, 4, 5, 6, 7. There we go. Potassium. You want to find potassium on the periodic table. Hopefully now we're getting a little bit better at finding them. Potassium, hey, look at that. It's in group 1. So I want to just draw the symbol for potassium nice and big. And then I'm just going to draw 1 valence electron. Now sometimes students ask, does it matter what side you put it on? Meaning I put it on the top, could I put it on the right or the left or the bottom? And the answer is it does not matter which side you put it on. You could absolutely put that single valence electron for potassium on any of the sides, as long as it's on top, bottom, left, or right. You don't want to go putting it diagonally. We don't put it at like the 11 o'clock position. We put it at 12 o'clock, 3 o'clock, 6 o'clock, and 9 o'clock. Next up, GE. GE. So first question, how many valence electrons, how many dots do I need to draw? So you got to locate it on the periodic table. Germanium. It is over here. It is metalloid, and it is in group 14, which means it has 4 valence electrons. So we're going to draw that GE nice and big. Then we're going to put 1, 2, 3, 4 valence electrons, top, bottom, left, right. And then we're done. Those are our examples right there. So that's Lewis dot diagrams. We are absolutely going to be using Lewis dot diagrams a lot when we're talking about bonding. And then the last thing that I want to mention before you start the group activity, I know there's a little bit more of the notes, but I'm going to finish that when I come back. Octet rule. Octet. Those of you who are in music have undoubtedly heard the word octave before, and hopefully you know, if you know music, that there are 8 notes in an octave. That oct prefix indicates 8. It's a prefix that means the number 8. So an octet is something that has 8 in it. And the octet rule is of absolutely fundamental import in chemistry. It says that elements like to have 8 electrons in their outermost subshells. Not necessarily overall energy level, but in the sublevels. Because if they have 8 electrons in their outermost sublevels, it means that they will have a full S and a full P. Remember, 2 electrons fit in S, 6 electrons fit in P. if they have that full S and P sublevel, it makes them stable, energetically stable. Having that full S and full P makes them stable. So elements, this octet rule, they're going to look at the number of electrons that they currently have, and if it's not 8, they're going to kind of do what they can to get it to be like 8, in terms of maybe they're going to get rid of some of their electrons, maybe they're going to try to gain some of their electrons. But octet rule is super important in chemistry, saying that elements like to have 8 electrons in their outermost subshells, meaning 8 valence electrons. Elements love to do this. If they don't already have 8, they're going to do what they can to get 8. So this is our stopping point for the notes. I know there's like a touch more, but I'm going to have you move on to the next page of your packet, which is the group activity. Okay, and that's talking about types of bonding. So make sure you follow the group activity. Do what it says to do. For the checkpoints for this, because I'm not here today or tomorrow, I want you to check, I want spokespeople, I want you to check with other groups and see if you guys came up with the same answer and adjust your answers accordingly. All right? So be good, because the sub will tell me if you're not.